We looked in the past at the double slit experiment. Alright, so in the double slit experiment, we said that there would be a barrier and then a screen. And we said that if the conditions were right, if you send in light waves toward the barrier, then we could get a maximum or a minimum of brightness on the screen depending on where we look at the screen. We said that if we looked right in the middle, then there should be what's called a central max. And the reasoning behind it was that the waves would be in phase as they approach the central max. Yep, just like that. But we also said let's say that the path lengths differed by half of a wavelength, like that. Then we said they would be 180 degrees out of phase, and you could get what's called a dark fringe. At that point, the waves would cancel out. So you might think, how could this possibly work with just a single slit? Okay, let's analyze that. Let's say we remove that middle section. And now we just have what's called a single slit. You might be tempted to think that there shouldn't be any fringes. There shouldn't be any bright fringes or dark fringes. You'd think that the light should just diffuse everywhere. Like it should just disperse to all points on the screen and there would just be light everywhere, right? But that's actually not what happens. And we want to see, why does that not happen? Alright, so there will actually be a bright central maximum. That is true. But there can be dark fringes. Why would this happen? Well, what you have to do is you have to look at the whole situation. You have to look at all the waves. Okay, so let's take the top of the opening. What would happen? Well, this guy could start at a phase angle of 0 and then finish up at a phase of 0 as well. But let's say that this guy at the bottom was a whole half of a wavelength longer as far as path length goes. Then you see the top would be totally out of phase with the bottom. So see, the top cancels with the bottom. But that doesn't tell the whole story. That's just part of the story. What about all the waves in between? Like, what about the wave that occurs halfway through, and the wave that occurs here a quarter of the way and 3/4 of the way. What would those waves do? Would they cancel with anybody? It turns out that they wouldn't cancel with anybody. And to show that, I can go to Desmos and make just a picture of the different waves that would appear, right? Okay. So in my Desmos window, I could start with the sine of t. I think I'm going to use x because the program understands x better. Yeah, let's just look at sine of x. Alright, that could represent the top waveform at the very top of the opening. And then what else would we have? Okay, sine of x minus pi. That could represent the bottom wave, right? Now we know that if we add these two things together, they're going to cancel to 0. So just sine of x plus sine of x minus pi. It gives us this green result, which is 0. But what if we include all the waves in between? What if we include, for example, sine of x plus pi over 8? Because if you look back at the picture, the wave that would occur here, they would all start at 0. And so, like especially at this point, halfway point, that should be 90 degrees ahead, you know, when it goes to meet the other waveforms. See, they all start at 0. But when we want to add them together, we have to go from a phase of 0 up to a phase of 180. With that in mind, we would have sine of x plus 2 pi over 8, sine of x plus 3 pi over 8, and so on. You can see what it's doing. And what's going to happen is we would add all these waveforms together. In order to determine how bright the light will be on the screen at this particular point. And that's our result. Alright, now what if we add all these together into one waveform? That could be tricky. Maybe I'll just give them all letters. Maybe the program will let me add them together. And the last one was this one. We don't need this one anymore. Alright, let's try a of x plus b of x plus c of x plus d of x plus e of x plus f of x plus g of x plus h of x plus I of x. As you can see, these waves don't cancel. But there's another interesting thing that happens too. Each of them has an amplitude of 1. But notice how the sum of 9 of them here doesn't actually add up to 9, does it? It adds up to less than 9. And that's because they're not in phase. And so this is what happens with the single slit phenomenon, is it's not as bright. as the double slit. Okay. What we'll get is we'll get a max. Like, we'll get a bright fringe here. But notice that it is a bright fringe when the path difference is lambda over 2. Remember that with the double slit, it was the opposite. We said that we would get a bright fringe when the path lengths were equal to a multiple of the wavelength, but we would get a dark fringe when the path difference was lambda over 2 for double slit. So that's a little bit opposite there. Alright, so the width of the slit for the single slit experiment is actually given the letter A instead of D in the formula sheets. You'll still have an angle theta. That's this angle here. And so this becomes A sine theta. That's the path length difference. A sine theta P equals P plus a half times lambda, where P is an integer. But starting at 1, 1, 2, 3, etc. This is where we'll have bright fringes. So what would cause dark fringes? Well, let's look at our barrier again. And we'll draw our lengths, path lengths. Now it may be surprising, but in order to get a dark fringe, what you would need is you would need to complete a full wavelength within A sine theta. Now why would this be the case? Because we want the top path and the bottom path to come out in phase. Now you might think, like, why in the world would that cause total cancellation? Like you can see here, these guys are going to constructively interfere. The top and bottom constructively interfere. But in this analysis, they are not the only waves involved. There's a whole range of other waves involved. This guy would complete half of a wavelength. So what's its phase? Its phase would be 180 degrees, and that would be the difference between the waveforms at the top and in the middle. And at the bottom, our phase would be 360. See, so every phase is going to be represented here. This one will complete a quarter of a wavelength before it gets to that boundary there. At this position, we'll complete 3/4 of a wavelength. And what's going to happen is the 90-degree phase is going to cancel with the 270-degree phase. So let's go to Desmos and see if that happens. So now what we have to do is just keep going. And just keep adding waves. Alright, you can probably see what'll happen now. We go back to our total sum and just now we want to just keep adding the new waveforms. And you can see what's happening, right? Until we get to our final result, which is, of course, 0. They cancel to 0. So we get a dark fringe there. That's the idea. Alright, so even though the top and bottom constructively interfered, everything else would cancel. And it would even destructively interfere with the one that's at 180 as well. Okay, so but ultimately all waveforms cancel. When A sine theta equals P times lambda. So we will get a dark fringe here. At these locations.